Hi there, and welcome back to the second video from chapter 2.5 about lines in 2D and 3D. So the previous video did lines in 3D, and we're actually going to expand that, or I guess you could say more like reduce it to the case of 2D. And these are going to be parametric equations for lines, right? I'm not talking about the standard form that you may have seen in algebra or algebra 2. I'm not talking about y equals mx plus b. That is one way to create a line in 2 space. I'm talking about parametric equations, right? And these are very handy, especially when you want to go from one point to the next. If you want to go from one point to the next and connect that with a line in terms of y equals mx plus b, that's kind of hard. It's very easy to do with parametric equations. But just like in 3D, our lines are defined by two things. We have a direction vector, all right, that tells me the direction in the x direction, y direction, right? And so once we have a direction, it's sort of like the slope, and then some point. So it's sort of like point slope. I get a point that this line goes through and a direction that it goes. And so once you have this direction vector and this point, you create the parametric equations, one for x, one for y, and you let t go from negative infinity to infinity. That basically creates the entire line as opposed to just a line segment, but we'll get to line segments in just a minute. Okay, so the important thing to notice about these parametric equations is that the direction vectors, their components get placed in front of the t, all right? A and b, so those are the coefficients of t, and this x1 goes there, and this y1 goes there, right? So that x and y go through this point, and then the line that is created is parallel to that vector. Okay, so now we're going to talk about intersections, all right? Sometimes two lines, and in 2D, you've probably gone through this in previous math classes, right? You can have two lines that intersect at a unique point. You can have two lines that are parallel that don't intersect at all, and then you can have two lines where one's actually on top of the other, and they intersect in infinitely many places. So we're actually going to go, in this first case, an example where the two lines do not intersect, but specific for this example, they do not intersect at a unique point, right? So this example right here is actually an example of two lines that overlap. But you'll see the similarity to something like this when we go through it. Okay, so, and you know, I only know that ahead of time because I see what's coming up. You wouldn't know that from the beginning. From the beginning, you just have two lines, line 1 and line 2, right? And if you look at the direction vector for each one of these, the direction vector for line 1 is 1 comma negative 3. Comes from the coefficient there and the coefficient there. And the direction vector for the second line is 3, negative 9. All right, and so what you should do is you notice that if you take 3 times v1, you get v2. So these lines are in fact parallel. But it's hard to tell right away whether they're the same line or not, right? Because, for example, if you let t be 0 in our line 1, so if we let t be 0 in our line 1, it goes through the point 1, 2. And if you let s be 0 on line 2, it goes through the point 3, negative 4. So they don't share that point in common, right? Neither of those points are in common. But you have to sort of figure out for what values of t and s do these things match up, right? And so in order to do that, we need to know where and when are the x values the same. So that's what this equation is. T plus 1 equals 3s plus 3. That's the two values of x. And likewise, the y values have to be the same too. So that creates these this single equation. Combined, we have two equations and two unknowns. The unknowns are t and s, right? So the first thing we'll do is we'll send the s's over that way and the constants over that way. And then we can put it in matrix forms. We already did this in the three-dimensional case. It's actually easier in the two-dimensional case because we have one less equation. Okay, so once we get it in this form, we can put it in matrix form, and then we try to solve it via standard Gaussian elimination. Right? And if you go through some of the row reduction, essentially you just take 3 times this row, 3 times row 1, and add it to row 2. And notice that turns into a 0, 0, and 0. So it all goes away. This last equation is now meaningless. And so what that means is we have infinitely many solutions, right? You fix a parameter for s and you get to choose t. So there's infinitely many solutions. Right, so what it's saying is that if you go back to these two lines, which are parallel, there are infinitely many places where they intersect. In other words, these two lines are the same. Right, so infinitely many points of intersection. All right, and so this is very similar to what would happen if they didn't intersect at all, right? Because if they're parallel, they could also not intersect at all. But what would happen in that case is if you had, you go through the row reduction, and then over here, instead of having 0 times s plus 0 times t equals 0, if that was, say, a 5, or anything other than a 0, if it looked like that, you'd have no solutions, all right? And if you have no solutions, then the two lines do not intersect. Right, so the intersecting in infinitely many places and intersecting nowhere, it sort of looks the same, except this last equation, once you get it into row echelon form, is either going to be zeros, all zeros and a 0, in which case you have infinitely many, or all zeros and a not 0, in which case you have none. And that happens when they're parallel. Okay, so since they intersect, we knew they intersect, we can actually find the angle of intersection, and it should come as no surprise that this angle is going to be 0 because they are the same line, right? So to do that, basically we have, if we have two lines, let's suppose they're not the same line in this case, then the direction vector v1 and v2, the angle between the two lines is the same as the angle between the two direction vectors. So that's what we're getting at here. And we use the cosine formula for the dot product to figure out what the cosine of the angle is first. And if you look at u and v up here, we got rid of them a second ago. Oh no, here they are. We'll call this one u and this one v. Alright, so the size of u is if we look at this, that's the square root of 1 plus 9. The size of v is the square root of 9 plus 81. So there's the square root of 10, square root of 90, and then when you take u dot v, you get 3 plus 27 is 30, right? And when you simplify this, you get 30 over the square root of 9. That's 1. Right? So the cosine of the angle between them is 1. That means that the angle is actually equal to 0. All right? Which we basically knew because they were the same line. Now, on the other hand, if we have two lines that actually do intersect at a unique point, we go through the same process. Again, we don't know ahead of time which situation we have, but it is certainly worth noting that the direction vector, and I'll call it u this time, is, let's see, 1, 3 for our first line, and the direction vector for our second line is 1, negative 4, and you can see that these two lines are not parallel. So we can expect to get a point of intersection, right, because this is 2D, not 3D. So you do the same thing. You set your x's equal to each other, set your y's equal to each other, and then you get all your variables on one side, all your constants on the other. Once you have it in that form, you put it into matrix notation. And the determinant, if you take a look at the determinant here, it's 4, minus negative 3, so it's 4 plus 3, which is 7. So we get a unique solution for S and T. And you can use Gaussian elimination or the inverse, however you want to do it. There is a unique solution. It's easy to find. You get T equals 2 and S equals negative 1. So you get a unique solution. And the point of intersection is actually found by taking T equals 2 and putting it into the line 1 equations. And so if you let T equal 2 here, let's just put that in. If T equals 2, then X equals 3 and Y equals 8. And down here, if S equals negative 1, then X equals 3 and Y equals 8. So that's your point of intersection. Right? The point of intersection is 3, 8, and you can find that by using either equation. It's probably good to check both to make sure you get the same point. And then the angle of intersection is found easily enough by taking getting the cosine first, using the cosine formula for the dot product. And in this case, u, which I've erased above, and v are given right here. You take u dot v, and you get 1 minus 12, which is negative 11. And then the size of u is going to be square root of 1 plus 9, square root of 10 down there. The size of v is going to be the square root of 1 plus 16, so that's the square root of 17. And, you can simplify it or not. There's really not much you can do with it. But you use a calculator or software to figure out the arc cosine of this. And you get 2.57 radians, or converting that to degrees, 147.5 degrees. All right, so that's the case. If the lines intersect at a single point, you get a determinant here of non-zero. If they intersect at infinitely many or none at all, you should note, like in this example, you should notice that the determinant is 9 minus 9, which is 0. So we either have no points of intersection or infinitely many. Okay, so the final demonstration of directed or line segments or lines in parametric form is in terms of a directed line segment. And they're great. They're really easy to build. So suppose I have a point P and a point Q, and I want the directed line segment that starts at P and goes to Q. It's really easy to create. And you think of it like, I think of it like this, where these are points, right? You're going to let T go from 0 to 1, and the directed line segment, when T is 0, so if that's 0, is going to start at P. But then, when T is 1, when I get P plus Q minus P, I end at Q. Right? And so that the math makes sense, we're going to, here we're sort of adding and subtracting points, which mathematically doesn't really make sense, but we can change it to, we can change this to a vector, right? Q minus P is just the vector PQ. And then we're still going to keep our point P. So we start at P, we end at Q. At Q. It's great stuff. But you don't really leave it in this form. You have to put it in parametric form, right? Where you have x equals something and y equals something. They both have t's in them. Okay, so the way we do that is if we have our points, say we have, so, okay, here we go. I was wondering where I had to find the point P. So if that's my point P, little p1, little p2, little p3. And we'll do it in 3D instead of just 2D. 3D is nice because you can use it for other things besides just going from one point to the other. You can go from like one color mapping. If you have an RGB color mapping, you can go from one color to another in 3 space, right? Okay, so if I want to go through this point and this point where I start at P and I end at Q, right, then I first have to create my direction vector, which is just PQ, right? PQ is the direction vector. And the terms in that direction vector look like Q1 minus P1, Q2 minus P2, Q3 minus P3. So that's my direction vector. Notice this is the first term. That's the x direction, y direction, z direction. And if it starts at the point P, then x starts at P1, y starts at P2, z starts at P3. Right? And t goes from 0 to 1. That's what makes it go from P to Q and stop at Q. If you let t go from negative infinity to infinity, it would go through both, but it would go, infinitely in both directions. Okay, so here's a nice, once we do an example, this should become all quite clear. Suppose I want a parametric equations for the line segment that starts here and ends here. Right? If this is P and this is Q, I want it to start here and there. It's really easy to do. Right? My direction vector is PQ, and you want to think Q minus P. So that's just 7 minus 2 and negative 2 minus 5. So it is 5, negative 7. Right? And it has to go through the point 2, 5. So there's the x2 plus 5t, y is 5, right? And negative 7 in the y direction. So it's really easy, right? And t goes from 0 to 1. Notice when t is 0, I'm at the point 2, 5. That's where I started, right? And notice when t equals 1, right? T equals 1, then over here I'm at 7, x is 7, and y is negative 2. That's where I ended. Very handy little trick. If you want to get from one point to another point, if you want to go from P to Q, you create the line segment, the directed line segment in parametric form that comes from P plus T times Q minus P. And then you just break that up into x and y, and if there's a third term, z. And you get your parametric equations this way. It's a great little trick, much easier to do than in the old y equals mx plus b form for a line, right? Those days are done. We're doing lines in terms of parametric equations. That wraps up this chapter, and I'll see you in chapter 2.6. Bye.